In a black hole, time stands still when you use a pole long enough. Into the interior of the black hole, what will happen? Imagine that you are standing on the edge of a giant vortex. The vortex is the black hole. It doesn't just distort space, it warps time, as if you were standing on a huge rock. And the pointer in this stone is almost near the black hole. It stopped spinning. Welcome to Lao Maoquest Society. In relativistic physics, space-time is a unified concept. Everyone's experience of time and space is unique. Despite this, due to our relationship with others, small differences in speed and attractive force field, our daily experience is at a macro level. The scale is similar. Black holes as extreme celestial bodies. Its powerful attractive force field significantly distorted the surrounding space-time structure. This distortion results in space and time near a black hole. The region farther away from the black hole. Qualitative difference. These objects exhibit similarities with classical physics. Expect different behavior. Exploring the impact of space-time warping on time. And we found out the attractive force of a black hole. Significant slowdown. Effect theory. Close. Observers of black holes experience time dilation. This means that compared to observers far away from the black hole, their time passes more slowly. This effect is especially noticeable in attractive force fields. But it requires precise experiments and observations to verify. Suppose we have a ship that can resist extremely attractive force. We can approach worlds of black holes. The world is a boundary of a black hole. Beyond this boundary, no matter or radiation can escape. Near this border, extreme distortion of space and time. The passage of time almost stopped. We can see through, measure the signal from outside the black hole. Time dilation, for example, a detector in the black hole's sphere of influence. Signal frequency emitted, due to the time dilation effect, will be observed to be higher than the actual frequency. According to general relativity, we can calculate the time dilation effect. Near the event world of the black hole, our time is relative to distance. Black hole detector will be significantly darkened. For example, at a distance of 1.01 times the radius of the black hole Shavasi place, the speed at which our time passes may only be probed 12% of the detector. This means that, for the detector, every last second, we may have been here 8.3 seconds. This time dilation effect is a direct result of general relativity. He demands light speed remains constant in all reference frames. In order to meet this requirement, space-time must be curved by an attractive force, resulting in a change in the speed of time. Interaction with the event world. Theoretically, once an object crosses this boundary, can't go back. If you stick a long pole out of the event world and pull it back, still an interesting thought experiment. He challenged our understanding of the laws of physics. Generally speaking, we have a very long rod sticking out of the dirigible. Then you can pull it back intact. The ends of our rod, it is part of a single entity. So when I move this part of the rod forward, the other end will also move at the same time. But here's what actually happened. You apply a pressure wave of electrons, pushing electrons through our rods at almost the speed of light. When we put our set of long poles down to the world time, the time closest to one end of the world, the one we're holding, is slow. So two things can happen. The first theory is that located in the world, pole of the world. The end perceives time moving away from him. Very fast, so when you push the rod towards him, he is very courier, receiving all these pressure waves from the electrons, then explode or break. But you can't observe this, because the light from the world is too red. The second theory is that, compared to the end we hold, around the world, time runs very slowly. This creates a very strong pulling force. It will break like a rope is carrying too much weight. This doesn't mean that if you fall into the world, you will be blown away or torn apart. It's just because standing still near the world and beyond are two completely different states of existence. If you let go, although time is approaching the world, the rushed parts of the world run slower. Matter has also accelerated, and it's faster than the parts of the world that are farther away from the world. Move faster. But our poles are like those on Earth. Complete down. This is the interior of a black hole. Interesting phenomenon of time standing still. As a science enthusiast, I recommend that you read about black holes. The key to understanding the universe is rated 9.8. He not only explained it in simple terms, the scientific principles of black holes, it has also brought us to the forefront of space exploration. This book will definitely satisfy your understanding of the universe and the curiosity of black holes. I am Brian Cox. I'm a professor of particle physics at the University of Manchester and the Royal Society, professor for public engagement insides, and amongst other things, I'm the author of the book Black Holes, the key to understanding the universe.